So during the presentation, I will explain the project formulation and the methodology that we use. Andrea instead will explain the result we got and some improvement that can be done to our solution. Okay, so the aim of the challenge was to provide a solution that maximizes both the accuracy and the energy efficiency, where the accuracy is the mean top one accuracy score, whereas the energy cost is the mean flop count in infrared phase. To evaluate the solution, we have to submit more models or more variation of the model. And we have to compute the area under the energy accuracy curve, as it's shown on the slide. To compute the area, we have to use the reference of the max energy cost, that is the efficient net B7 that is shown in the slide. The dataset we have to use to optimize the solution is the tiny ImageNet dataset, which is a subset of the ImageNet dataset and contains 100,000 colored images and 200 classes. And the images has a resolution of 64 by 64. So, considering the project statement, we have the first idea that we got was to train simple and basic models and to keep the resolution low and use different augmentation techniques. This methodology has some advantages. For example, that the simple models have less parameters, that low resolution of the images keeps the flop count small, and also that the augmentation techniques doesn't improve the flop cost in infrared phase. But this methodology has also some challenges. For example, that simpler models are more difficult to train and generalize worse than powerful ones, and also that training from scratch a model needs careful tuning and optimization of the hyperparameters. So here are shown some of the architecture that we tried. For example, AlexNet, VGGNet, ResNet, ResNext, and some of the augmentation techniques that we tried. For example, horizontal or vertical flipping, rotation, and scaling, and so on. We also tried some more advanced augmentation techniques, for example, mix-up, which is a combination of images by blending them together, or cut mix, which is a combination of two images by cutting and pasting different patches of the different images, or, for example, local augmentation techniques that takes different patches of the same image and apply transformation to these patches. Here are some results of this fourth step. We choose the best model from the accuracy point of view, and this best model were ResNext 50 and ResNext 50. For the augmentation, we use some simple random horizontal and vertical flipping. And for the more advanced augmentation technique, we saw that the cut mix performed better. Here are some examples of the accuracy we got. We can see that using augmentation and also the cut mix, we improve the accuracy both for ResNet and for ResNext. And we can see also that ResNext perform better than ResNet. Another thing is that we try to improve the size of the images from 64 to 128. And we can see that there is an improvement, but we decided not to improve more this resolution because it also increases the flop count. So from these results, we observe that training the model from scratch is a good starting point. And with the augmentation, they reach a good accuracy, but it's not what we want. So we notice two main problems. The first one is that the low resolution of the images makes difficult the classification task and also the training for the classification task. And the second problem is that to have better accuracy results, we should increase the amount of data for the training. So the first solution we tried was to use pre-trained models. For example, models that were trained on ImageNet dataset and retrain them on the tiny ImageNet dataset. This is a good idea that we had because tiny ImageNet is a subset of the ImageNet dataset, and also because ImageNet dataset is bigger, have a bigger resolution, and more classes, so it's easier to retrain the models for the tiny ImageNet one. And then, speaking about the efficiency cost, we apply early exit. This we tried this method to try to reduce more the flop counts. Early exit is a method that consists in adding different exits to the network and computing the score, the entropy score in this case, which is a sort of confidence metric we can use to control if the prediction can exceed the network earlier, and so reducing the amount of energy cost. Yeah, this is the methodology that we use for the solution, and now Andrea will explain the result we got and the further improvement that we can do. No.
Okay, thank you, Luca. And hello, everyone. I'm Andrea, as Luca introduced me. And this is the part in which I will show you the results and the further improvements. So the first slide, here we can see the final results for what concerns the accuracy that we got. So here we can see that the model are still ResNet 50 and ResNext 50 because they are the models that scored the highest results in this sense. You can see here that we used the augmentation, the cut mix, the resize, and also the early exit. For what concerns augmentation and cut mix, they just improve the accuracy because you are just adding data to your training set. Then, for what concerns resize, it also increments the accuracy, but we have to be careful because the resize also if we resize the images, and so we have images with a higher resolution, our model will take more time to evaluate them, and so we have a cost in terms of gigaflops, which is higher. So we have to be careful. And then the early exit. As you can see, the interesting factor of the early exit is that it's not just a method that lower the number of gigaflops, but it also increases the accuracy. So you can see in the case of ResNet 50, I don't know which one is the pointer. In the case of ResNet 50, you can see that in the case without early exit, you got an accuracy of 64. Using the early exit, you get other 7% of accuracy more. So the early exit is not just a method that decreases the cost, the efficiency, decreases the cost in terms of gigaflops, but also increases accuracy. Here, we are comparing our models to, let's say, the literature. And we have found this site, which is Papers with Code, that is just a catalog, a classification of the model that are used on this particular dataset and also other dataset But for our case, for tiny ImageNet, we see that ResNext 50 scored 72.39 of accuracy. And instead, our models scored 82% of accuracy. So there is an improvement, and probably due to the early access. Then we can start to talk about gigaflops. So here in this graph, you can see that there are all the models that we have trained. These are ResNet 50 and ResNet 50. And on the right side of the graph, you can see that there are the models that are resized, that works on the high resolution images. And you can see that the count in gigaflops is higher because they have to process high resolution images. And the models that are trained on low resolution images have a lower count of gigaflops. The best model that we have trained is here, is a ResNext 50 model with 82% of accuracy and 2.5 gigaflops of consumption. And here you can see that there are a lot of models because the early exit produces a lot of models, one for every threshold that you set. So if you want a model which is very precise, you set a high threshold, which means high gigaflops. If you want a model which is not so precise, but his consumption is lower, you can lower this threshold, and you have another model. Then we can see that choosing the best model that we found, we can draw the metric that Luca told us before. And we can see that the area under this figure is 31.73, which is a value that can be compared with EfficientNet, which is a value that can be compared with the score of EfficientNet on ImageNet. And EfficientNet is a very good model of efficiency and accuracy. And this ends the part about our results. Then we have a small section to talk about possible improvements for this method and things that we have not tried. First of all, I'd like to talk about early exit once more. First, it's interesting how the early exit improves also the accuracy. That's probably due to the fact that since there are more exits, the first layers, because maybe there are some, we receive more gradient signals. The standard signal from the normal network, and also some signals from all the exits. And so these layers will have more signal, and so they will create features that are more able to catch images and classify them. And also another improvement that can be done with early exit is using another hyperparameter, which is the position of the exit. So when you are training your model, you can select the position. So you can sorry, you can put this exit whatever you want, and look which position is the best one. And then now leaving early exit, we have found these results in a paper recently that I have highlighted here below. And it is an idea which comes from physics. And the idea is to define a kind of temperature on the network. And so the temperature in physics is defined as the average value of the kinetic energy. So 1/2 velocity squared by the mass, but in this case, there is no mass. Also the Boltzmann constant and so on. And how we define this velocity? The velocity is the velocity of a weight. So if you compute the first derivative of the value of a weight, and you say this is the velocity, then you can square it, you can compute a sort of temperature. So you can classify every filter in the network, and you can say what is the number of weights. So it's the average. So you divide by the number. Yeah, you can compute it for a filter, for the entire number of network, whatever you want. So you have this temperature. You can classify the filters in the convolutional network, in the convolutional layer, as a hot filter or as a cold filter. And here, the results that are present in this paper, using a network which is LANET on the MNIST dataset. You can see that the original model scores 98.8. And if you remove the two hottest filters, so the one with a higher temperature, you got still 98.52%. So the accuracy is not decreasing, but you have two filters less. And since LANET has 6 filters, if you remove 2 filters, it's a lot of filters that we're removing. And then there are other results, such as that if you keep only the coldest filter, you still get the 3 coldest filter, 88%, which is a good result with just half of the filters. And if you keep just the hottest filter, you have just 20% of accuracy. And this is just a paper that we found interesting also for the contest, but we didn't have time to reproduce it. This ends our presentation, and thank you for your attention. And if you have questions, we are here. Yeah.
Probably not the solution. Increasing the resolution in the trial, the convolution with this like high dimension.
Yeah, we tried that, but it was too difficult because the parameters change a lot the solution when we try to train the model from scratch. So at a certain point, we just decided to do some other thing without instead of optimize every single parameter. So we changed the approach.
Maybe yes, also. Yeah, I was when you said regarding the early exiting.
Yeah.
That there are 2 gradient signals. I mean, multiple.
Yeah, multiple.
I'm just wondering if you could put like kind of weights to.
Yeah, you can. Yeah, it's possible. When you define the loss, you say my loss is the sum of this loss, and every loss for every exit, and you can weight as you want. You can say this loss is more important than this one.
Yeah. We also tried to change the weights of the losses, but we didn't have time to try or
there was no such improvement in the end. We just used the equal weight for every loss.
Or say we didn't mention the threshold for cardiacs, like stability. So
that's so easy. Since you use the model, you don't have to retrain the model if you change the threshold. So you can try every threshold you want. We just used a lot of threshold, no pilot in space threshold, a lot of threshold, and we just choose the best one.